Welcome to our second press conference today, and it's on droughts and floods in a warming climate. And taking part in this press conference, we have Lorenzo Alfieri, who is a researcher at the Institute for Environment and Sustainability at the European Commission Joint Research Center in Italy. Wouter Gruel, sorry if I'm mispronouncing that, is a researcher at the Wageningen University and Research Center, Earth System Sciences in the Netherlands. Yusuke Zato is a postdoctoral research scholar at the International Institute for Applied Systems Analysis here in Vienna. And Debbie Paulson is a research associate at the University of Edinburgh in the United Kingdom. And I'll now hand over to our speakers. Thank you.
Thanks for the introduction. Well, recent research shows that at the current emission rate, the target of limiting global warming to 2 degrees by the end of the century is more and more unrealistic. So scientists are urged to assess the consequences of high global warming scenarios, so typically around 4-degree warming, on the future flood risk in Europe. This is now possible thanks to the recent release of the latest high-resolution climate projections over Europe. But what we did in this study is not to simply rerun previous approach with this new scenario, but we did a number of changes that we believe brought to the current approach to a really high level of physical consistency for such large-scale risk assessments. So what we found in our study is that the future flood risk in Europe, in terms of damage and population affected, is likely to be higher than what previous studies suggested. And this, so typically more than 200% increase by the end of the century, just due to climate change. And this is due mostly to a substantial increase in the frequency of extreme floods and not just to the magnitude, as previously stated. So I'm going to quickly go through the main novelties of the work that we have carried out. I grouped them into 3 groups because there are a number. So we have technological, scientific, and technical advances. The first part, the technological advances, is basically we are using, as I said, the latest regional climate projection at high resolution over Europe and corresponding socioeconomic development. We're also using the latest version of high-resolution exposure information of land use and population density in Europe at 100-meter resolution, and corresponding information on flood protection level on the European rivers. But the key points of the analysis are the scientific advances that I don't want to go too much into details, but the key points is basically we're using an event-based assessment to account for changes in the frequency of floods and not just the magnitude. Then I think for the first time in this type of such large-scale assessment, we are using flood inundation maps at high resolution, which are derived by a physically based 2D hydraulic model rather than by normal simplified approach that they were done before. And also the bias correction of climate scenarios is done not yet on the atmospheric variables, but on the impact assessment, which also has a number of advantages as compared to previous approach. And all of this was possible thanks to a number of technical advances that we carried out to improve the computing and the handling of such a large data set over Europe. How do we know if the model works well? Well, we ran the model using an atmospheric data set of observed climate at high resolution over Europe that we have at the European Commission. So we saw that the current model is able to reproduce the damage of past floods as compared to observed figures for the past year. So we have simulated the past 24 years. And also as compared with the figures reported on population affected and damaged by the European Environment Agency, we have average estimates which are within 15%, which is very good for this type of assessments. So since the model seems to perform well, we applied it on a future climate scenario. Now, I don't want to go into the details of this slide, but the key point is that what we found, if we look at average exceedance of extreme event, well, large event above bank fault condition, which are potentially dangerous, we see results as found as in previous work. So decrease of frequency in some basin in Scandinavia, an increase in the other river basins like in the Po River. But the interesting thing is that now we could analyze the full spectrum of magnitude of events. So the interesting thing is that when we look at really extreme events, like above 100-year return period, we see a consistent increase of the frequency of these extreme events more or less everywhere. And this is particularly important because these extreme events are often above the flood protection level of European rivers. So when we include these results into our impact assessment, we want to estimate the damage and the population affected in the future as compared to the baseline. We use an ensemble approach, meaning we have simulated 7 different scenarios to evaluate the consistency and the agreement of the different models. And we look at the results for the current climate and particularly to the future, analyzing 3 different time windows centered in 2020, 2050, and 2080. And the interesting thing is that we found this, as I said before, this substantial increase of damage and population affected by the end of the century, which are more than 220% in terms of by 2020, and about 150% increase by 2050. So it means that if today 100 people are affected, in 280 it will be 320. So I'll conclude here. Thanks.
Which one is it?
In this folder? I don't know. On the desktop. Yeah, this one.
This one.
I'm going to present results of a study which studies the consequences of climate change for water in Europe. This was done in the context of a EU project which is called Impact to Sea. The general aim of Impact to Sea is to look at the consequences of climate change for various sectors which may be affected by climate change in Europe at a time of 2 degrees centigrade warming. I'm involved in the water calculations of this project, and we did this by a multi-model study. The idea behind a multi-model study is that if we do many calculations, we get information about the uncertainty in the calculations, and it has also been shown in several other studies that a multi-model mean is often better than any of the contributing projections. The results, the main results of the project are that in Europe, under 2 degree warming, river flow, mean river flow will increase north of 45 degrees north, which is approximately north of the Alps. And this is caused by an increase in mean precipitation. Then, in terms of seasons, in winter the changes are larger, and the changes in precipitation and river flow move further southwards, so that also parts of the Mediterranean area get an increase of river flow and precipitation. In summer, changes are generally smaller. The most noteworthy change is that mean river flow decreases in high mountains like in Norway and the Alps. And then as far as the extremes are concerned, river flood will increase in magnitude south of Scandinavia, according to the projections, and it will decrease in magnitude in the northeast of Europe. A few interesting, strong, specific aspects of this study is that we focus on Europe, and this allows us to use high-resolution model results from regional climate models, whereas many of earlier approaches to compute this were done with global circulation models. And yes, so we have a higher resolution. Then the other strong point is that there's a large number of simulations, 455, and as far as I know, there has not been done earlier on a study focusing on Europe with so many simulations. Specific aspect of the study is that we compute the changes at the time of 2-degree global warming and not at for a fixed period like 2020 to 2050. And one should realize that this means that in the different climate model simulations, this period happens at different times. So it moves from simulation to simulation. Also within Impact2C, we integrate with other sectors. In Impact2C also the changes in the climate are studied, and the results of the water projections are or will be used in computing changes to hydropower, for instance, to cooling water for thermal power plants, changes in snow tourism, mainly in the Alps, and we will also compute the economic loss due to floods. To conclude, I have 2 slides with graphical presentations of the results. This is a graph showing changes in the mean. The upper left panel shows the changes in precipitation, and the most noteworthy feature, I think, is that the blue area signifies that's the area in Europe where precipitation will increase at 2-degree warming. And the effect of that is that river runoff will increase and also evapotranspiration will increase more or less in the same areas. You can see that the patterns in the 3 panels are more or less the same. So the extra water coming in from precipitation will increase evaporation and increase runoff in the same areas. So precipitation is really the main driver for the changes in river flow, mean river flow, and mean evapotranspiration. The final slide shows the changes in floods. And this is the change in the magnitude of a once in 10-year flood. It's a relative change. We see the red or the green part of Europe. There, the flood magnitude will increase according to our projections, and this is because extreme precipitation is going to change in these parts of Europe. In the northeast, the magnitude of the floods will decrease, and that's because here there's another process working. The extremes in precipitation are not that important there. Floods are due to melting of snow in spring, and this will decrease because there will be less snow in future due to lower temperatures. Thank you for your attention.
Good afternoon. I'm Yusuke Sato, postdoc research fellow in YASA in Austria. Today, I'm going to introduce an impact assessment of climate change impact on hydrological drought. We have 2 key points. One is renewed sense of urgency for adaptation and its regional differences. Now we are in the process of establishing global goal of adaptation and mitigation policy, and we put a milestone on 2030 and 2050. But the world is not equal at all, so we need to acknowledge the regional difference of urgency. I'd like to begin with this key figure. This map shows the timing of the onset of the unprecedented hydrological drought. In other words, this map shows how long we have time to prepare for the expected change. In this research, we presented a new method, TPCD. TPCD stands for Timing of Perception Change Regarding Drought. This index shows the timing at which future drought will deviate from historical experienced range, and never return for a certain period. In this figure shows that time series of drought days, and the line shows historical range, and this point is TPCD. And this is the first estimate of the time regarding time left for extreme event. This you can find many quite early TPCD around the world, shown by red shade. For example, west side of USA and Chile. So we concluded our analysis indicates 13 of 26 regions show significant signals of unprecedented hydrological drought until 2050. So we concluded that the timing that some regions have left to prepare for change is short. We need strategic planning and prompt action. This is our messages. This result is based on the long-term continuous offline simulation. We use 2 RCP scenarios so far and use 5 GCMs. Actually, we had to remove 2 RCP scenarios from this presentation because I found some errors. So we are in the process of updating the result before publication. And in this study, we found the hotspot of climate change impact of drought in upper figures and warmer color. These regions would be our hotspot of drought. This figure shows difference between end of 20th century and 21st century. This is a ratio. And we estimate the uncertainty of this drought simulation. This slide shows the result of the inter-RCP scenarios comparison of TPCD, and black dot shows ensemble mean, and the other color shows each GCM, and the left column in the figure is RCP 2.6 and the right is 8.5, and no TPCD point, for example, in this figure is no dot means no TPCD, and please note that TPCD around late of 2019 is meaningless because the deviation period is too short. From this figure, you can find different future between RCP 2.6 and 8.5. But on the other hand, this is for the case of the deviation period for 20 years. In this case, even in the case of RCP 2.6, you can find early TPCD around these hotspot drought-prone regions. Okay, this is end of my presentation. These are my key answers. Thank you.
Okay, so I'm Debbie Poulsen from the University of Edinburgh, and I work specifically on trying to detect the influence of human activity and changes in historical observations of precipitation. The work I'm going to be talking about today is a study that we did looking at changes in the monsoon. So what we showed is that over the last 50 years there's been a decrease in monsoon rainfall, and that is attributable to emissions of aerosols. So a bit of background in that there's been a number of studies that have shown that global precipitation has changed because of the influence of either anthropogenic combined forcing or, in general, greenhouse gases. So whereas greenhouse gases will tend to cause precipitation to increase, aerosols will tend to cause them to decrease. Unfortunately, the patterns of these changes are very similar in space and time, which means it's actually quite difficult to separate them. But quite a number of studies had looked at different monsoon regions, and they had connected the decrease in monsoon rainfalls to the emissions of aerosols. So what we decided to do was to take all the monsoon regions in the Northern Hemisphere and analyse them as a whole. So that's the region that you can see plotted here. This is our analysis region. We look at the May to September precipitation in this region, and we analyse it from 1950 to 2005. So the top plot here, the black line, shows an observational data set. So this is the CREW data set. And in the black, you can see how from the 1950s to the mid-1980s, you get this real decrease in precipitation and then something of a recovery through the 1990s. The bottom plot shows emissions of aerosols for the whole of the 20th century. And I'm showing that because I want to kind of highlight how in 1950 you get this real ramp up in the emissions, and then kind of a leveling off and then it decreasing through the 1990s, and that's Europe and the United States beginning to clean up their pollution. Also shown on the top plot are the results of some climate models. So we took models from the coupled model into comparison project. So we have a large ensemble of models, and by averaging over all of, so these are the historical models, you'd say, of the 20th century with all the historical forcings, so all the greenhouse gases, the aerosols, the natural forcings, such as volcanoes. By averaging over all these models, you get rid of the uncorrelated variability and you're left just with the forced response, and that's what you can see in red. And you can kind of see that it has a similar shape, that it's sort of decreasing through from the 1950s to the 1980s and then a bit of a recovery afterwards. But of course, there's a number of different forcings that go into this. So what we've also done is look at the individual forced runs in the models as well. So this is the result you get for just the greenhouse gas forcing, and you can see here that if you look at just the greenhouse gases, you get just an increase in precipitation during this whole period. So it doesn't seem very likely that the greenhouse gases are responsible for these changes. For the aerosol-only runs, however, you can see that it very clearly has a very similar shape. So again, this decrease and then something of a recovery. And we also look at just the natural forcings as well. So this is mainly volcano and solar. And what you can see is that although there are variations from year to year, which is largely volcanic eruptions, there's no overall trend, really. So what we actually do with all of these is to combine them in a very rigorous statistical analysis, the details of which I'm not going to go into. But what we're trying to do is see whether we can actually attribute the observed changes to any of these individual forcings. And we do that by accounting for the large uncertainties you get with the internal variability of the climate. And what we find is that really it is the anthropogenic aerosols that are responsible for this overall change. And that's a pretty robust result. So I'm showing one observational data set here, but we actually repeated this for 4 separate observational data sets, and they all give the same result. So it does seem a fairly robust result. And just to put this in a bit of other context, this is a third in the number of studies that we've done. So we also looked at changes over zonal mean changes over land, and we showed that changes there are attributable to the greenhouse gases, and that's largely increasing rainfall in the mid and higher latitudes. We also have this change in land and ocean with the wet and dry regions. Again, this is the greenhouse gases, but in the monsoon regions, it really does seem to be the aerosols that are driving the changes. Thank you.
Thank you very much for your talks. We'll now open the floor for questions. Are there any questions from here? Okay, well, if there are no questions, you are welcome to approach our speakers, and you can book some of the interview rooms if you want to have interviews with them. And we'll finish here for today at the Press Center. But there is an event on an unveiling of some Mars Express images, some new large-scale images of the Martian surface. And this is downstairs in the blue level. And there's a DLR press release outside if you want to have more information. And the next press conference is on recent and future changes in the Greenland ice sheet, and it's on tomorrow at 12 o'clock. Thank you. Thank you.